All right, let's take a look at calculating the heat of reaction from molar reaction enthalpy. So this is a chemical equation. We've seen this before, right? And we can refer to it a couple different ways. We started out saying we got two mercury oxides reacting to form two mercury atoms and oxygen gas. Then we switched to moles and the concept of moles, and we could say 2 moles of mercury oxide form 2 moles of mercury atoms in the liquid state and 1 mole of oxygen gas. And so when we talk about moles, there's a lot going on. So there's a lot of reactions. So we can now think of this enthalpy as part of this equation. So there's some heat either going in if it's endothermic or out if it's exothermic. So we're going to explore that. And this is per mole of the reaction. So for every 2 moles of this, there's 182 kilojoules absorbed. In this case, because delta H is positive, that means it's endothermic. If delta H is negative, it's exothermic. So absorbed, and this is released. So combustion, you might see a combustion reaction. Some sort of fuel plus O2 forms CO2 and water. Those are going to be exothermic with a negative delta H. And again, this is part of our stoichiometry now. For every 2 moles of mercury oxide, there's 182 kilojoules absorbed. For every 1 mole of oxygen gas, there's 182 kilojoules. And so we can write this as a conversion factor. And this is in kilojoules. So there, you can actually, this is, if it was exothermic, you could feel it. If it was just 1 molecule, you could not feel it. But as we get into moles, so if you get into billion, you can feel it more. Billions of billions, you can feel it more. A mole, you can feel it at the macro scale. So that's why we're in moles still. So this is per mole of reaction. So let's take a look. As I already talked about, this is a positive delta H. So this would be endothermic. Now, suppose we have 96.9 grams of this mercury oxide. Will any heat be released or absorbed? Yes. In order for this to happen, for that reaction, it has to be absorbed. Now, this last part is the stoichiometry part. So we have a specific amount. We have grams, but we don't do chemistry in grams. We do chemistry in moles. And so let's figure out how many moles of this mercury oxide we have. And then we can determine how many kilojoules exactly will need to be absorbed. Okay, so mercury is 200.59 grams per mole. Oxygen is 16. So we add those up, we get 216.59 grams per mole. So let's do this. We go 96.9 grams. Every 216.59 grams, 1 mole of mercury oxide. That's our molar mass. So this is our stoichiometric relationship. And we're going to say whatever's out here, we're going to put down by it. So every 2 moles of mercury oxide for every 182 kilojoules absorbed. Now, if I had done oxygen, it would be 1 mole of O2 down here. So you have to use whatever's in front. And again, we can do it for any reactant, any product, just like stoichiometry. So we get 40.71 kilojoules. Now 3 significant figures, and we got 40.7 kilojoules. There we go. So endo-exo, that plus or minus is going to give it away. Released, absorbed. So released goes with exothermic, absorbed goes with endothermic, and then using stoichiometry to calculate exact kilojoules.